Hello everyone. So in this lecture we'll try to build this um, back propagation that you see, right, completely from scratch. So just to give an overview of, right, what is back propagation. So in simple terms, if I have to say, right, think of it as if we have an equation like z is equal to a into b plus c. Okay. Now, the z variable rise, it's it depends on a, the value of b, and the value of c. So, what backpropagation helps us with, right, is to show the impact of change in a on z, impact of change in b on z, or impact of change on c on z. So that if we say if we want to increase the let's take a different equation, something like this. So if you want to change the value of z, right, if we increase the value of a and b, the value of z will increase. But if we increase the value of c here, right, the value of z reduces because there is a negative sign in between. So it's fairly simple equation that you are seeing here, but it can become pretty complicated, and you can have all whole set of equations and log exponentials and everything, all of those things. So and basically this is the one, the back propagation is what is used to train the neural networks and everything. So we will go ahead step by step and reach that stage where we create a neural network and then train with our back propagation. Okay, so for the time being, right, let's get started. So before that, right, I would just like to explain the differentiation. What do we mean by differentiation as such? So so usually how we define derivative, right? I think this is a pretty good example. So say this is how we are defining our variable, right? So let's say we want to see um, with change in a, right, how does the value of z changes. That's what derivatives helps us with. So so we can say it this way, that say a is 4, b is 2, c is 1. Okay, so that's how we calculate c, and we print c. Okay, so we get the value of 7. Let's take this, and what this equation says is f of a. So let's take at a as a variable. So so f of a is when we put the value of a here as say 4. This is what we get the value of 7. Now we need to increase a by h, and h is fairly small. Okay, so here we can take h as one more variable and make it like pretty small. Okay, and we do this, and let's change the variable to say, let's set underscore and print it. So if we, oh sorry, that's a mistake. So because in board mass rule, right, this would have got calculated before, so that's why you see that variable. So we want to increase. Okay, so we increase the value of a by a very small bit, multiplied by b, and then c. So we get the value of something around this. As I told, right, if we increase the value of a by a small bit, the value of z, the output changes. Okay, now derivative, right? What we do, fa plus h minus fa by h. So that means, so z underscore minus z h. So this is the derivative. So two things are important here. One is the sign of this. Okay, it's positive. What does that signify is if we keep increasing the value of a, the value of z increases. Um, that's a positive correlation, we can say. More so, the value of its 1.9, and so impact of increase in z is this much. Um, let's now try to increase the value of c. So we'll take this again, but sorry. And rather than doing this, right, let's keep it that way and increase the value of h and see how it impacts. Okay, so you see the value got reduced. Now if you want to again calculate this, right, one thing is important is the negative sign of it. It shows that if we increase the value of c, the z value reduces and the amount and everything that is there, right? So so this differentiation is one way to identify if we change certain value, right? How the value of z changes. So usually you would have seen we usually write d dz by d, say a. So that's what it shows us. This is what the value we will be getting in there, that how the value of z changes with respect to a. So so that's one thing. Now let's try to build a class which helps us calculate this gradient value with respect to the output variable c. Okay. For the time being, I will keep that as it is. Now select the name of the so we'll name this as class value. And just to give you a context, right, all of this that you are saying, right, means actually Andre Karpati did the same thing. He 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 has a video on this backpropagation from start. I have done this like 2 or 3 times as of now, and I hope that when I'm teaching this, right, finally I do minimal errors. But anyway, let's go ahead and see how that goes. Okay, so class value I have defined. So if you go ahead from above, right, few things you would have seen. One is for each of these variables, right, few things that we want to specify is what is the value that it will take. So we can specify it using data. Okay, so self dot data equal to data. And one more thing that I want for each of these variable is the gradient, this thing for each of these variable, right? Something like dz by dA. So that is the gradient. So self dot grad we will calculate. As of now, initially we are putting it as a 0. Okay, so we can define a is equal to value a, right? Sorry, value 4 b equal to value 2, c equal to value 1. Okay, and this comes along a plus b, so a into b plus c. Now the thing is, we are not able to calculate these values, right? Because now a is, it's not an integer, it's a value type. So let's overload these. Sorry. Um, self other. I will explain in a bit what I'm doing. Um, and the same will define for multiplication as well. Multiplication as well. Okay. So it says we can't add in with a value. Okay, so the thing is, this is something also we can take into account, but for the time being, right? But anyway, let it be ABC. So interesting. Multiply, but see, it's saying support not reduce int and value. Okay, so it's d, it's taking as a value. Is it? Oh, sorry. So there is a mistake. So what I'm doing is I'm overloading the plus value because we can't add value variable, rather than we can only add positive. So what I'm doing is, when this multiply is getting called, this is what is getting called. Okay, so a into b, or if I have to just show, right, a equal to value. Okay, let's take this. Okay, and if we do a into b, right, sorry, here also I'm mistaken. Okay, so usually what happens, right, it returns you a variable of type value here. So if you want to print, sorry, not that in, I think. the way to thing like this was there. Present self print. Okay. And return this as an okay. So so we took two value variables, okay, and we took value variables and called them null. So usually what this means internally is a dot underscore null underscore this, and it gives you the b value. So self goes a, other goes b. We take the data, multiply it, and again return a value. So you get a value variable itself that is coming out, but when we are going to print, right, it usually calls this function, and this is what is getting printed here. So data and everything. But if I just comment it out, right, so see, usually it returns a value variable which is not returning a pretty good looking output. So I've put it in this way. Okay. So the same that goes on here. So when we do d equal to a into b, right, the object is returned with 8 in it, and then we are trying to add it, and that's what we are getting in C. So that's what you get. So 4 into 2 plus 1, 9. So that's the value variable that we have defined. Um, One more thing, if you want to do, right, or something to learn is a plus 2 if you want to do. Say uh, at some point of time we just want to add an integer value to it, right? Usually it fails because um, it returns, sorry, like this. Now the problem that is happening is this other, right, is getting 2, and 2 is an integer. It doesn't have a data value. So how do we handle such things? So usually what we do is r- see, it works. So now you can add integers as well to a value variable. So usually what happens, right? First it calls this one obviously, and it sees that okay, um, other other it takes, and then it sees is other an instance of value. Yes, return the other as it is. If no, wrap it around value and then go ahead with that. But where it will fail is um sorry. So here it passed, but you will see this will fail. Why, you know? Because this is what is happening here, okay? So when it is calling, right, self should be, or this should be a value variable, but this is just an integer. So to get around this, right, in Python we have something known as a um r add or reverse add or something like this. So what usually happens, right, when we call this, right, it tries to call this and it sees that okay, it can't call this variable, so it looks for this r add variable and switches. So when it calls this variable, right, it does it this way, a 2. Okay, that's what when this gets called, right? So self gets a and this gets a 2, and then again obviously this internally this is called. So now self is again a and 2, and this goes through this and everything, we get the answer. So that's why this um, just now it worked right. um Not sure what's happening. Okay, it worked now. Let's use something like plus b. It's working. And the same goes for the multiply, okay? So you can put this for multiply as well, okay? So what will happen is a into, sorry, 2, sorry, wait, and define a, see, now it works. But the problem is 2 into a won't work because again the same problem. So we need to do the same thing. How we defined it for that variable. Well, it works, and then it should work as well. Okay, so that's that. So we have got pretty much the addition and the multiplication. So one thing I'd like to have is how you can visualize this thing, okay? So I will just copy paste a code. If you want, I can put it in the chat as well. It's not something I want to delve a lot of time upon, but this is this way it helps you visualize what we are seeing as of now. So let's remove this bit here. Okay, so draw underscore dot, and we can pass it C. Okay, value does not have attribute previous. Okay, so this is something I wanted to teach or I wanted to tell you later, but one thing is we need to also track the child nodes from where this value came. I will explain that in a bit. Okay. Okay. So whenever we call these values, right, we need to pass something like this. I will explain in a bit what is that. Need for this. Here. Let it be that way. In a bit, I will explain what is that. So this is the variable. This is the okay. Operator is also not there. Uh, let's put that as well. Okay. So let me explain what all things I did here. So this is the C that you are seeing. One thing more we can do is one thing more we can do here is put up a label as well. Label as well. The label is this thing that Z and this thing comes. So let me explain what all I have done. So this is a way to visualize this tool. It takes into account the the label, the data, and the gradient that is. And the reason why I added first this child node is right. It's a bit um something you should understand. So what is happening is, say when we want to calculate um Z, right? Uh, Z's gradient, it's fine. We can do it something like dz by dz, obviously with respect to z. Okay, everything will be real, so that will be 1. Okay, if we want to calculate z with respect to t, right, so something like dz by dt, let's say we want to calculate this, right? What will be this value? D for us is A into B. Okay, right? D is for us is A into B. Okay. And again, we don't have any correlation with respect to this variable. So what we do is we define Z as D plus C equal to D plus C by dd. Okay, and what dd by dd plus dc by dd. Okay, so what is dd by dd? That is 1 plus dc by dd. Does the value of c change with respect to d? No, right? We are directly giving a value. It has no impact on the value of d, so that will be 0. So that will be 1. Okay, and the same if you do for dz by dc, right? dz by dc, right? That will also come out as 1. Now the interesting question is, if we want to calculate dz by da, okay, how you can do that? Because we know, or let's do that itself. So dz by dz is 1, right? So we can put it like z dot grad equal to 1. Okay, because dz by z is equal to 1. So when we do this, right, see, you get a 1. Okay, so gradient is 1, means if we change the value of z by 1, say 10, the data becomes 10, its value changes to 10. So okay, that's that way it is fine. One more thing that we saw is d dot grad. This means the impact of d on z, that is again 1 we calculated, and the same way we calculated for c dot grad, that is equal to 1. Okay, so what I mean by that is impact of d on z, impact of c on z, something like this what we were calculating, right? This gradient. Okay, that's what is happening there. Now we want to calculate the impact of a, right, on z. What is the impact of a on z? Now one thing we know is impact of d on z. That's the only thing as of now we know. We don't know anything with respect to that. So something that comes in differentiation is the chain rule. So if I have to explain it in a simple terms, right? So if we are calculating dz by dx, right, but the value of z depends on y and the y depends on x, right? So we can just multiply those two differentiations. So very good example here is given. If a car travels twice as fast as bicycle and the bicycle is 4 times as fast as the walking man, right, then the car travels twice into 4, 8 times, so it easily gets multiplied. So in the same way here, right, if you want to calculate dz by da, right, so we see first what is d is impacting which variable. It can impact the d variable. Okay, so dd by da, one thing we can calculate multiplication. Now d impacts the value of z, so dz by dt, so that will give us dz by dA. Now if we want to calculate, right, so dz by dt, so impact of d on z, that is already one we have calculated, and dd by dA, right, let's do that calculation. So d is for us a into b, a into b by dA. Okay, now it will be 1 into the that's a multiplication rule in differentiation. Okay, so what happens is A into dB by dA plus B comes out B into dA by dA. That is the multiplication rule in differentiation. You can look up to that. So anyway, 1 is getting multiplied. Anyway, we can keep it for the time being. Okay, A into dB by dA. Does the value of B gets impacted by A? No, right? So that's 0. Sorry, that's 0. Sorry, let me keep it again. Yeah, that is 0 plus now B. Okay, value of B into dA by dA. What is that? That is 1. Okay, so 1 into, I will remove it. A into 0 becomes 0. B into 1 is B. The same way if we do, right, dz by dB, that will come as A. Okay, so this is the chain rule. So why I have included the children node, right? So what the children node specifies when we are doing, say, this addition operator here, right? So not addition, let's say multiplication first. It's happening first, multiplication is happening. So I'm telling that D is the parent node and it has two child as A and B. The same way when we are trying to calculate Z here, right? Z here, we are telling it that it has a two child node as D and C. Now why is that important is, if you would have seen here, right? If we trying to calculate the impact of A on Z, right? We should know two things. The impact of Z on D means this whole picture from here. Okay, means from here, right, everything that has happened. So this gradient, it might happen that there are multiple equations, but we are interested in this gradient. That's what we plugged in as 1. Okay, and the local gradient means this gradient, the impact of A on D. Okay, so this one that you are seeing here, right, it's 1 because here we are seeing 1. If D dot gradient was 10, it would have been 10 as well. So so what we are doing here, right, is just keeping track of which variables are impacting which variables. So Z, when we see, right, it has impact from D and C. D on the other hand is an impact on D and C, so that when we do these chain rule multiplication, right, we know how to break this or how to create this, where we say the impact of A on D, D on Z, because we have the tree structure aligned in terms of the child nodes that is it's storing. Okay, so and that's what we are printing here as well. So if you see, right, for every node that is here, right, we look into in terms of what are its child nodes. And means that's what this trace thing that you see, right, it does here. It looks upon each node, tries to find out its child nodes from this variable and tries to add it up. So it's sort of a tree structure we are trying to form with each of the parent nodes, so that we can calculate these gradient, the impact of these variable on this variable on this, or something like that. Okay. So now one thing, interesting thing, if I have to tell you, right, if there is an addition, right, usually you will see, right, this gradient gets percolated here. Same you can see here. But when it's a multiplication, right, uh, a dot grad, sorry, a dot grad, when you are trying to do, right, um, it comes out as B. 1 into B, I usually try to keep that in mind. Okay, 1 into what 1 is here is the parent node gradient into the local gradient. Okay, so when I say local gradient, I mean dd by dA, and when I'm what I mean by parent gradient is the impact of his parent on the C. Okay, that way. So usually when we are talking in terms of the multiplication, right? So parent gradient is 1 here, so we can write it as d dot grad into the local gradient we calculated, that came out as 1 that came out as b. Actually b means the other variable that is there, so b dot, oh sorry, that's the value, the gradient, right? Hmm, got it right. So this was gradient of d, that is d, impact of d on z, and this is the local gradient that came out to be b, that is the b. In the same way we can calculate b dot gradient, that will come out to be again the parent node and the other variable value. Okay, sorry, it's saying, oh, it's data, sorry, it's data, it's data. Okay, so what we get here is a dot grad is 2. Okay, sorry, a dot grad is 2, b dot grad is 4. So that's what we get, but let's see if the values that we are getting right are true or not. So we'll do this using this thing. Okay, this one, this one, this one. Okay, so so this is the variable. Let's say we are trying to change at a here. Okay, oh sorry, we can remove this for the time, or we can print it. So f is coming like this here, and this is f plus h. Don't take the way I'm writing it, it looks pretty pathetic, but I think you understand what I'm trying to do here. So it is z underscore and um, gradient is coming as this. Okay, so see, which is near about 2. Okay, if we change the impact of a on z, that's what you see here, gradient is 2. Let's change the value of b here. Okay, mm, okay, see, you get near about 4, that's what you are getting here as well. Let's change the value of c as well. It's -1. Oh, okay, sorry. So here I have taken addition. What I can do is add a subtraction as well here. As of now, we haven't defined subtraction, so I've taken as d plus c. So if I want to have a subtraction here, right? Um, hmm, not other return, it will be cell plus minus other. It's addition of plus minus other, but the thing is we need to define the negation as well. Neg self return minus 1 into, sorry, self. Okay. So what is happening is we are using the addition itself, where we are saying do addition of self and minus of other. But again, minus of other, minus of value, it will fail. So we are calling a negation when this will be called, and what we are doing is multiplying minus 1 with self. So now everything is handled, I believe. Yeah, so a into b is 4 into 2, 8 minus 1, that is 7 here. Okay, let's um why we got two multiplications here? Okay, okay. So see, one thing is happening. Interesting thing is, so A into B happened, but A into B happened for sure. That happened, and we got the values as 8 here. Now the C, right? That was here. That was C supposed to be here, right? It got multiplied first with minus 1 because we did here multiplication with minus 1, right? So everything is forming a node itself, and we multiplied it, and then we got minus 1. So minus 1. So it should be actually be a C, but uh, oh, that is not a C anyway. That is minus C. So we can't specify it from there. But anyway, so C got multiplied with minus 1. That is what minus C we got. And then the addition happened and we got 7. So if we change the value, right, it's minus 1. So let's go ahead and do that. So um, z dot grad will be 1. Okay. D dot grad will be anyway 1. And these all remains the same because this nothing has changed here. Now if I want to calculate the C part, right, that is the impact on Z by C. Okay, so Z is defined as D minus um it has become a bit complicated here. If you want to see the impact of C, right, again you need to apply chain rules. Impact of this on this variable and this on this variable, like that. So let's give it a name. We can call that as let's take m is equal to, sorry, so C is defined, right? So C is already defined. Okay, so C is already defined, that is C is equal to 1. Okay, um, this variable, let's say, is n equal to -1. M is equal to -1 into c. Okay, and so z is equal to d plus m. Getting it right? Z is equal to d plus m. So what value will come out is, oh, sorry, yeah, so 7 it came out. Okay, 8 minus 1 is 7. Now let's calculate this. If you are getting confused, right, just let me know. Okay, so um, dz by dm we want to calculate. Okay, m is this variable here. So d, again, because this is addition, right, just now we learned it. Just now we learned that the gradient percolates, right? So it became 1d. Uh, these all got calculated, everything. So if it's a plus, right, usually this gradient comes here. We can do that calculation if you want. So d plus m by dm, that makes it dt by dm plus dm by dm dd by dm. D has no impact on this variable, so that's 0 plus dm by dm is 1. So the same thing happens. So that becomes a 1. That gradient, I don't have a handle on that. Okay, in the same way, when we are trying to calculate dc, sorry, dz by dc, right, because it's a multiplication, right, we learned that this gradient, that is, or we can say it as impact of c on m, then m on c. Okay, so impact of c on m, so dm by dc into dc by, sorry, impact of c on m, impact of m on z. Okay, so impact of c on m and m on z. So dz by dm into dm by dc. So dm by dc and m. Okay, so impact of c on m, that is c on m, and m on z. Okay, that's what we are trying to calculate here. So dm by dc will be m is -1 into c, that is minus c. So d of minus c by dc into, this is the local gradient and this is the parent gradient, the one that we calculated here. Oh, sorry. Sorry. See, impact of c on m and impact of m on z. Okay, don't get confused. So impact on c on m is dm by dc into impact of m on z, that is dz by dm. Okay, so dm by dc is the local gradient that we calculate here, so that will be d minus c by c into dc by dm, that is what we have calculated here, that is anyway 1. Okay, so d minus c by dc, anyway you know, is -1. So c dot grad will be equal to -1, and the same thing we got here, -0.999. So It's working fine. Okay, if anyway you got confused, right, just just let me know. Okay. So that's it. So we are able to calculate the gradient and everything. Now, one thing is, rather than doing it manually, right, uh, let me add a function here itself that helps me calculate. So if I want to calculate the gradient of D, it calculates for me. B, it calculates for me. Okay. So um, dot is backward equal to so now this is an interesting question that we need to answer. What do we mean by that? So when we reach this, or when this function is called, right, when we are in this state. Okay, let me simplify this a bit. I don't want to complicate with the minus signs for the time being, right? Let this be an addition and this be that way. Okay, so when that plus is getting called, right, this means we are in this state where we have D as self, C as other, and that operation is happening, and the Z we are getting, that is in out. Okay, so if we are calculating backward, or if we are defining backward, right, or if we say uh, D dot backward or something like that, right, uh, usually here that we saw, right, when we usually do a backward and when it's an addition, the parent gradient just percolates inside. Okay, but there is one interesting thing, because the equation is so small, what something we are not observing is, let's take um, m is equal to a plus b. Okay, n is equal to m plus um let's say k. Let's use different variable just so that I don't confuse. A f. Okay, getting it right. So a is equal to value, give it any value, 3. F is equal to value as 2, k equal to value as 1. Okay, and we are printing n. Sorry. Okay, and if we do this right, this is oh not C, sorry. Um, let's add this as well. E. Okay, so it's E F K M N. Okay, so this is oh, sorry. No, So this is what we are getting here, right? Now what I wanted to say is, let's say at any point of time, right, we are calculating, say, df and the impact on n, okay, all our additions. So df dn by df, impact of f on n, okay. So it follows the same rule in terms of local gradient addition of the parent gradient, okay, because here parent itself was z, and so the impact of z on d we directly calculated. But here if you want to calculate this, right, so what this will be according to the chain rule is impact of f on m. So dm by df into dn by dm. Got it? So impact of f on m, impact of m on n, okay. Again, so my main story is that this is again the local gradient, this thing that we need to calculate, whatever that comes in, multiplied by the parent gradient that is there, okay. So here if we have to calculate, right, the that will be anyway 1, okay, based on the plus rule that we learned there, right, usually the gradient percolates here. So dot grad will be equal to 1, okay, dot grad will be also equal to 1. The same thing that we learned here as well, right, that the gradient follows, whereas here as well, right, um, uh, the same thing will follow, the same gradient will be percolated here as well. So here, right, we don't need to depend on um, um, this sort of a calculation that we did during the multiplication time. When there is an addition, right, we can directly take the parent gradient and put it in there. So when we define here, right, when we are trying to calculate for, say, d dot backward, right, that means the gradient of this we are calculating, what we'll do, just we'll take the parent gradient and put it up here. So okay, so what will happen is self dot grad equal to, which is the parent here, parent is the out, yeah, that's the value we are creating. So out dot grad, okay, and self dot underscore backward equal to underscore backward. Got it? And that's the reason, right, we first initialize z dot gradient, because if this is not initialized, how, if it is a plus, then we can easily pick this up and put it up there. Or during multiplication as well, you again see you need the parent gradient here as well. So when we are calculating a dot grad, right, we needed obviously the b dot data value, this value, but we needed again the parent gradient. So when we are doing this back propagation or something like this, right, this is what is known as back propagation, where we calculate this gradient, then we calculate these two gradient, then we calculate this gradient. So that's why the tree structure is important. That's why we were storing this child nodes as well there, okay. And if we have to do for multiply, right, just give a thought how it will be. Just pause the video and think what we can put in here. So that is the state when we are saying a dot gradient we are trying to calculate here. So what will happen is we need to take the out dot gradient, that is the parent gradient we need to take, multiplied by, oh sorry, I'm doing it the wrong place. Here is some multiplication. So here doing multiplied by the other, that is there, take the data of that. That's what we did here, right? So parent gradient we took, d dot gradient we took, and then the other variable which a was getting multiplied, right? We are multiplying with the data of this, so 2 into 0. Okay, so that is what it is. I hope it should underscore backward is okay. So this is this is just to get the data correctly, right? Okay, sorry. So it usually is lambda none. So by this we want to say, as of now we are initializing is this with none, but wherever it gets initialized, right, this is how it will get initialized there. And anyway we don't need to need to pass on self here, because anyway we have that here, so we can use that. But just let's take a look if it works or not. Okay, so we do, so initially when we do a z dot gradient we need to initialize that, because there is no operation that is happening here, right? Neither addition or subtraction. When we do d dot backward like this, sorry, okay, so that's where the thing is. We can directly call this, we don't need this. Okay, d dot, so when I do this, right, and if you run this thing, see, you got d dot grad as 1. The same thing now. So one thing you would be seeing here is, right, when I do a c dot backward, right, it's not getting calculated, or how the value of impact of c on z. Mm, let's do the other ones. A dot backward, b dot, oh sorry, okay. Again, if we see here, right, just to say a got calculated, so this 2 is coming from b dot data into t dot grad. Okay, so that's why you see here 2. But interesting thing one is b is not getting calculated, neither c is getting calculated. Can you find out a reason why that is happening? So what is happening is, right, when we call a into b, right, a dot underscore mul underscore b, right? When we call this, right, a is the self here. Okay, a is the self here, and b is the other. So here a is the self here, b is the other. So a dot backward we are defining here. Okay, so because self is a, right? But what is the other? For the other ones we don't have anything. So what we need to do is we need to use um um okay, one thing, that is what will be the gradient of this, because for the other also it needs to get calculated, right? So the same goes here as well, but any um, uh, so one thing we can, so one thing we can do is I need to see what might be the good way of doing this. Okay. So here as well for the other as well when we are doing, so it will be self dot data during the multiplication and other dot underscore backward equal to underscore backward. Still I'm not very happy with this, but I'm not sure. There's one way to solve this, but I will try to figure out the dot grad equal to so whenever that backward gets called, right, everything will get called. Again, not a very great way, but okay. So this happens here. We can do x d dot grad just for the time being have all of this x doing c, then v, and then this guy all got calculated. Let's see. Okay. Reason is because I didn't initialize it right. It took 0 0 here and then 0 all got multiplied. So if I initial z dot grad, it will come as a 1 and then the other, right? So one thing understood, right? So now it's a hacky way. If I'm calling c dot backward, right? That is self dot backward. So self is calculating his own grad, but the other grad, whereas when we call the other as well, it calculates both of them. Anyway, we'll see how to what is a better way of doing that. But anyway, so that is what is back propagation. Let's say we subtract it now. Okay, so z dot grad is 1. So back we will back propagate now. We calculated all of them. So here again we see 1 gets put into here. Anyway, when we did d dot backward, it got initialized, and c dot backward, it again got initialized. But anyway, then a and b all got initialized. This all got initialized, so minus 1 and everything. So that is what is back propagation from scratch. In the next video, right? Because this already looks pretty long, and just let me know if you have any doubts regarding this. Put it in the comment section. So next what we'll do, right, rather than calling one by one, one by one backward propagation, right, we will just write one method, that is z dot backward, and it will calculate all the gradients for us in that case. Actually, we can do that now itself. So one thing that you see here, right, mainly this trace that you are seeing, right, it is something known as a topological sort. So the thing is, it takes care of the dependencies, as you saw now, right? If we have to calculate d, right, we should know the gradient of z. If we want to calculate b, right, we should know the gradient of d and then the local gradient and everything. So in that regard, right, what it will do is it will try to put, first it will put z, then it will put d, and then it will put a and b. Okay, so that we take one by one. First calculate z, then calculate this, so that, so which all gradient needs to be calculated before, right? And afterwards and afterwards, right? That chain of how we should, which all nodes we should calculate the gradients, right? That itself will give. So this mostly comes from this here. So let's define a backward here, and sorry. Okay, leave the trace and everything. So it takes the root nodes. Wait. I don't want to miss out. Don't need to calculate edges. Okay, I will explain it in a bit. This is something that is required. So we usually use set so that it doesn't take any duplicate elements there. So that's the reason. Okay. So when the backward gets called, right, and it will be called by an object. Um, so I'm just looking into the code. Topological is this, and nodes at that one. So what it will do is it will go one by one, check if that we have already seen that node or not, put it up there. Uh, if we have not seen, go here, put it up there and pick up its child node and again call and everything. So in that way it will try to form the structure to it. And here child, I'm just copy pasting this code. But if you have any doubt regarding this, right, just let me know. Okay. Build, so it will call this, it will go through each of the parents and everything and all of that it will do. Self dot grad. So for the parent when it will be called, because for parent will call, right, for z it will be called. So what we do here, we first initialize that by 1 because anyway we know that will be 1, and then for nodes, and so how it is storing is it will store a b then d and then z. It's in ulta, it's in a reversed order. We need to switch it back so that z comes up, then d comes up, then a and b and everything. Okay, that's why that logical dot backward, it should help us solve this. So so let's initialize this first. This is like this. This is what we got. All gradients are 0. This is also, it's not required now. Mm. One was for child. Yeah. Child build builds one thing I did miss. mistake is set dot child. I think this should. No, it's not add. Sure. Just not associated with Okay, I got it. So child is defined here, right? Outside the scope, actually this should be we. Yeah. So all the values are defined. This is one. This gets populated here because of the differentiation, and then for this, right? For calculating this, we take this data, multiply it with this, comes here. So same as B, we take this data, multiply it with this variant, and it comes here. So that's how we calculate the backward propagation here. Interesting thing what I saw just now, right? So there won't be that is something pretty interesting, I believe. So for A, right, uh, if you call A dot word here, it will calculate the backward gradient for this. Interesting thing that I saw here, right? If you want to go ahead with this, right, the parent node itself, um, so when we are calculating D, right, it actually calculates for these two individual. When I calculate for this gradient, right, it calculates for this individual. So in that case, we can get across this data here. So what we can do is if we put out dot backward equal to backward, right, and we remove this, and the same we do here as well. And if we remove this, right, what is happening now? So when it's getting called, right, so z dot gradient equal to 1 is where it went. Z dot gradient is getting called, right. Then it's calling self itself for gradient is 1, and then it is calling the backward function for that. So it will call z dot what is the this thing there, plus is there, right? So it will call this addition here, this, and the parent node itself, the out node, the parent node itself, right, will calculate for the two of its child node here itself, so that the values will be formed here itself when we are calling the backward for this. So when this backward calls, it will call for this because it will know itself and it will know the data of these ones. So that's one thing I learned now, that then it solves the problem of child nodes as well. So if you are anyway confused anyway, right, just let me know and go through this once. You should be able to as well. So here, right, we implemented the backward propagation completely for this piece of code. For each of the nodes it's calculating. In the future, right, we'll see how we can create a neural network and how we can train the model and reduce errors and everything. That will be in the next this thing. Here we can do yeah, the backward and everything. Anyway, let's do it in the next one.